Hello, it's Ahmed Fathy, and in this video I'd like to show you some Python programming and some visualizations for the whole PCA section. In this Python notebook we have the following: PCA, dimensionality reduction and whitening. Let's see what I have done here. Here I am importing NumPy, Matplotlib, and the math libraries. Then I am defining the mean and covariance matrix of my original data. So the variance in the x direction is 40, the variance in the y direction is 20, and the covariance is 10. Here I am getting the eigendecomposition of this covariance matrix into two matrices, the diagonal matrix and the eigenvectors matrix. Then I am generating some random multivariate normal distribution, which is a Gaussian distribution using this mean and this covariance matrix, and I am generating 10,000 data points. Here I am plotting the original data. I am plotting the vectors, the eigenvectors of the covariance matrix, and I am also plotting the original data points. And by this plot, I just want you to see how the original data points are oriented, and I want to prove graphically that the eigenvectors are actually the directions of the maximum spread of data. So here is the first plot right here. This is the data plotted, this is the first eigenvector, and this is the second eigenvector. And indeed, the direction of the eigenvector is in the direction of the maximum spread of data. So after that, we do the following. I want to perform the PCA rotation. So I multiply my original data points by E transpose. E transpose is a rotation matrix. I also multiply my axes by the same rotation matrix E transpose because I want to rotate the data points and the principal axis at the same time, and after that I replot my axes and my data after rotation. So when I come here, I find that the plot after rotation will be something like that. So this shows that indeed E transpose is the rotation matrix that we should multiply by in order to remove the covariance in our data points. After that, I want to perform projection or dimensionality reduction. So I come here, and after this rotation, I make a copy of my rotated data into this variable, and then I remove the second component from all the data points. I set the second component from all the data points to 0, which is equivalent to removing the second component of all the data points, and then I print the rotated data and the projected rotated data, and I see the following. For the projected data, I have those data points right here. And after I perform projection, the second components turn out to be 0, just as desired. Now, after that, I plot the data after this projection. So, plot after projection in the rotated space. So here, instead of the rotated data, I plot the projected rotated data, and we see the following result. Here is the result after projection, and it is indeed projected onto the x-axis, which originally was the E1 axis, the first eigenvector axis. After that, I want to show the projected data points in the original space. In this space right here, I want to show the projection of those data points onto this first eigenvector. So to do this, I rotate back using the E matrix like that. So here, I multiply E by this projected rotated data to get the reconstructed data in the original space, and then I plot the reconstructed data in the original space, and I see the following. Here is the result. Here is the data projected onto the first principal axis as desired. So by this, we have performed all the steps for PCA dimensionality reduction. Finally, let's perform PCA whitening. We have seen before that the whitening matrix is equal to d power negative 1/2 multiplied by E transpose. So I define this whitening matrix right here as NB, the square root of the matrix D. Then I get the inverse of this function to have d power negative 1/2, and then I multiply this by E transpose. After that, I multiply the whitening matrix W by the original data in order to get the whitened data. And then I plot the whitened data in the original space, and I see that this is the result, and indeed this data is whitened, just as desired. See you in the next video.